This will be available to you after today's session. I'll probably send it off to Asia, and then she can forward it on to you guys. However, if you would like the link directly after today's session, by all means, you can send me an email here, jack.flowjo@bd.com, and I'll go ahead and send that out to you. Okay, I like the data set that we're going to be using today because it's pretty straightforward and it has enough colors to see some differences between samples. So it should be good to kind of walk through and give you a good idea of what's going on. Okay, so let me give you just a couple of slides here that go over the analysis workflow, and I'll talk about that major difference, as I mentioned earlier, that exists between your standard immunophenotyping and the use of these tools. Okay, so the general workflow looks like this. You're going to clean up the data normally, like you would in any other scenario. Make sure you've got you get rid of debris, dead cells, doublets, things of that nature. And then after that, I highly encourage you to go ahead and add metadata to the workspace, because you're going to use these keywords to segregate the different experimental variables that you have in your setup, right? So, for example, you guys might be doing a long-term study over, I don't know, let's say it's got like 5 or 6 different time points. You have different aged cohorts of either mice or people. And of course, you've got 2 different sexes of mice and people, right? And then you may have, who knows, you may be subdividing the people, based on whether or not they've had an operation in the past or not, right? Whether they've been treated with a certain type of drug or not in the past, et cetera. There may be a lot of different experimental variables that you have. You want to incorporate all of that information as keywords. So I'm going to go ahead and show you how to do that today as well. Kind of written in orange here is my optional step for downsampling. Downsampling does a couple of things for us. There's a couple of advantages. Number one, it makes it very easy to make comparisons between samples because it normalizes the numbers of cells between samples, right? So everything can start essentially at the same number of T cells or same number of antigen presenting cells, whatever it is that you want to look at. So that's one advantage. The other advantage of downsampling is that some of these tools like TISNI and UMAP, they tend to be a little bit slow in terms of processing time. And you will notice this if you try to process a TISNI plot that has, let's say, more than 1 million events in it or more than 1 million cells. You'll know that you can take a coffee break for a little bit, go set the computer to go and then come back. So downsampling actually just reduces the numbers of events that you're going to feed into the TISNI algorithm or into the clustering algorithms downstream. And so it speeds up the process a little bit. Okay, so let me take a look here. Okay, so all right, no questions in the chat box as of yet. Okay, so adding keywords and then downsampling is an optional step, but it's a good one. Again, because of those 2 advantages. Now, after we do these steps of adding the metadata and doing a little bit of downsampling, there is the ever popular concatenation step. Okay, concatenate simply means to merge. So this is the step that separates the use of dimension reduction tools like TISNI and clustering tools in your workflow from a workflow that doesn't involve these tools. Okay. Anytime you intend to use TISNI or Phenograph or FlowSum or anything like that, and you want to make comparisons between samples, you need to merge the samples first into a single concatenated file. Okay, we do this in FlowJo, and I'll show you how to do it momentarily. Okay, but this is the primary crux, the primary bifurcation point. This is what makes using these tools a bit different than your standard use of FlowJo. And I mean, this is true for any other software. So if you guys were using R, for example, to do TISNI and all this other kind of stuff, you would have to merge the FCS files that you wish to compare first, and then go ahead and run TISNI and everything else, okay? So we're gonna go ahead and concatenate. And after we concatenate the files, I'll probably run some form of dimension reduction. We have TISNE, we have UMAP, and TriMAP. There's 3 different forms, essentially, of dimension reduction that are available to you. It's kind of up to you which one you rather choose. I'll get into a little bit more detail about the 3 different methods here in a moment. But let's continue with the workflow. Okay, so after running TISNE, et cetera, we'll go ahead and run some of the clustering algorithms and just see how well the clustering tools sort of cut up the data. We may be able to compare, let's say, what the clustering algorithms do to our manual gates. The other nice thing about, clustering tools, I should probably explain what a clustering tool is, first of all, rather than just explaining to you that we're going to go ahead and use them. So I apologize for that. So clustering tools you can think of as just automated gating. That's all they do. They auto gate your samples. And they are said to be unsupervised or unbiased, right? They don't have any sort of forethought or any structure about the algorithm that sort of tells the algorithm, oh, well, this data set has T cells and B cells, so look out for those, right? They don't have that kind of information in them. So the clustering algorithms come at it like, hey, I see that these cells have a lot of markers in common, so I'm going to group them together. And I see another set of cells that has a lot of stuff in common, and I'm going to group them together. In any case, you can use these clustering tools for a couple of reasons. Number one, if you've got a lot of legacy data that you need crunched, clustering tools can, analyze the data fairly quickly. But there's usually going to be a difference between what you manually gate and what the clustering algorithm sees. So there's always this sort of lag phase where you have to go back and see what the clustering algorithm did compared to what you did with your manual gates, right? How well did the clustering algorithm find my, let's say, rare population of B cells or something like that? Okay, so it's fast at crunching data, which is really nice. But the other advantage I think about using clustering tools is that they have a unique ability to see the data in multiple dimensions all at the same time. And as a result of that, they oftentimes can catch cells that are sort of in these transition states where they're sort of between 2 different phenotypes, right? And a lot of times this will happen with certain cytokines. You may see that, in the beginning of your stimulation cycle, the first 2 hours of stimulation, you start to see some activation of, let's say, TNF or IL-1. And then after 8 hours, everything is TNF and IL-1 positive. But in the middle time points, there's this trajectory of these cells that are, becoming inflammatory, or they're starting to, upregulate certain cytokines or perhaps downregulate certain lineage markers. In any case, these tools, the clustering algorithms, a lot of times are good at picking out these transitional state cells. And so I would use them just as kind of a fresh pair of eyes, a fresh perspective on the data to, look out for some population of cells that maybe I will not capture when I create my manual gates, right? Most of the time when I create my manual gates, I'm kind of doing plus minus, and I'm not really paying in much attention to cells that are moving from one transition to the other, unless, of course, that is the focus of my study. Okay, but in any case, they will provide you that kind of information. And we should be able to see some of these phenotypes today in today's data set. Okay, so really cool tools for analyzing or chopping up the data very quickly. But then you have the trouble, once these clustering algorithms are done cutting up the data, you have to figure out what the phenotypes of those clusters are. And so there is a series of tools that will help you with this. One in particular that I like is this one that is displayed here in the center of the screen. That one is called the Cluster Explorer, and it includes a heat map as well as a line trace diagram and some other features within it that will allow you to identify the phenotypes of these clusters, and also whether or not these clusters skew towards one experimental condition or another. So it's an extremely powerful tool. I'll show you guys how to use that. Hopefully you'll make use of it, okay? And then of course, you ultimately want to be able to identify differentially expressed populations, right? And pull those, figure out where those populations occur in which samples, right? Do they come from disease patients, healthy patients? Do they occur in the spleen, the liver, the lymph node, et cetera? So all of these tools will help you sort of work through that kind of a workflow. This slide just kind of describes the the plugins that we have available and whether or not they are dependent on this statistical package known as R. So the good news is there are at least one from every category here that does not require R, which is really nice. So if you wanted to do downsampling, run Tisney, and do some clustering and explore those clusters today, you guys could do it without any additional R setup. Okay, there are some that do require R. But don't be afraid of that. If you have any difficulty installing these things, we'd be more than happy to help you do that. And each one of the plugins comes with an instruction manual that shows you how to essentially install the R-related packages. So if you are going to use those tools, there is support there for you as well. Okay, and then the last slide I was going to cover here, I'm just going to kind of zoom down to this one. There's several different types of dimension reduction, and people always ask, well, which one is the best method to use, blah, blah, blah. Okay, the bottom line is these dimension reduction tools are visualization tools. They really help you to identify differences between two different experimental conditions, right? So if you've got healthy versus disease, or you have treated versus non-treated, right? Or wild type versus knockout, something along those lines, you overlay them in Tisney space or UMAP space or TriMap space, and you should be able to see the phenotypes that are unique to one condition or the other. Now, the way they display their data is a little bit different. Okay, Tisney, I like to characterize this one as, kind of looks like a bunch of little islands, right, that are disjointed or separated by white space. So the islands correspond to a distinct phenotype of cells. In the case of UMAP and TriMap, the islands are not, they're still separated by white space, but what UMAP and TriMap tend to do is they tend to group together cells that are more similar to one another. They put them closer together in that two-dimensional space versus what Tisney does. And give you an example here. If you look at the CD8 T cell population, which is kind of outlined here in blue, you will notice that in Tisney, there are at least 3, probably 4 or 5 separate islands for the CD8 T cell population, and they're kind of spread apart from one another, right? They're in different locations. One's in the northern hemisphere of the plot, the other one's in the southern hemisphere, et cetera. Okay, but in the case of UMAP and TriMap, they sort of bunch all of those CD8 T cells together in one section of that two-dimensional space. Okay, and then they have projections that kind of emanate from those islands that kind of give you a hint about the trajectory of those cells becoming, maybe they're stimulated with something and they're becoming inflammatory T cells, or perhaps they are developmental stage T cells that are not yet, let's say, fully differentiated, and they're on some sort of trajectory, usually moving towards some other island. Okay. In that case, like if you're studying cellular trajectories and you want to see how one type of cell kind of moves to another type, UMAP or TriMap may be more visually intuitive or more visually pleasing that way versus Tisney. Okay, I'll give you the other example here of B cells, right? You've got several different islands of B cells in the Tisney plot. And you can see here that this B cell population is completely separated away from the other B cell populations, right? With CD4 T cells kind of occupying the middle here. Okay? Whereas in the other two plots, you can see that all the islands are sort of juxtaposed to one another. Now, in my opinion, this is just my opinion, okay? Again, this is just based on personal preference. If I'm doing a study where I want to identify phenotypic differences between two different conditions, I prefer Tisney. And the reason I prefer Tisney is because it does a better job, in my opinion, of segregating out distinct phenotypes of cells away from each other. I don't care when I'm using these tools that all the B cells end up in one sector and all the T cells in another. All I really care about is whether or not I have new phenotypes popping up, or different phenotypes, I should say, popping up as a result of me treating the cells with something, right? Or the animal with something, or the patient with something. So in my opinion, I like the nitty-gritty nature of t-SNE over that of UMAP and TriMAP, but in more recent days, you will see many more publications probably with UMAP than you do with t-SNE. And, you know, again, it's just a matter of personal preference. If you like to see that the cells are moving along some sort of trajectory, it may be more visually intuitive to use the UMAP information. Okay, embed sum is another algorithm that we do make available. It is my least favorite of the three, and I think you can kind of get an idea as to why. The islands here that embed sum creates are rather fuzzy. It's hard to tell where the boundaries are between the different islands. I don't particularly like this, you know, really fuzzy edge to try and figure out, oh, what are these cells right here versus the cells that are out here. I think t-SNE does a really great job of bunching them together and saying, hey, this cluster over here, those are distinct cells, a group of cells versus the you know, sort of island that's down in the middle. So just my 2 cents. Again, it's up to you guys what you want to use. We'll take a look. Maybe we'll have the opportunity here to take a look at 2 different outputs. This is just the same 3 that I had talked about before, but with some clusters overlaid on top of them. Okay, so let's go jump into FlowJo and try to see how this stuff works. I'll check the chat box here real quickly. Let's see. There's a question, if I'm not too early, where do you access these options you are talking about? Okay, I'm going to show you right now. So the options to run dimension reduction and run the clustering tools and all that kind of stuff, these are located within the workspace tab, populations band, and you'll see this plugins drop-down menu. Now, t-SNE is actually built into FlowJo. So if you just wanted to do some dimension reduction without having to add anything more to FlowJo, t-SNE is already there. But in the case of the plugins that do clustering, maybe you want to do UMAP or TriMAP, all of these things are located underneath the plugins drop-down menu. Now, in order to get these plugins, what you do is click that drop-down menu and then click the top option that says FlowJo Exchange. Okay, and this will take you to our FlowJo Exchange website where we host all of the different plugins, right? So you go ahead and you find one that you like. FlowAI is a nice cleanup tool. It's small, so I'm clicking on this one because I can show you an example relatively quickly. You unzip the zip file that comes in, right? You see here it says FlowAI v2.3.zip. All I did there was double click on it. If you're on a PC, you normally have to right click here and say extract or extract all, something like that, and then give it a location as to where to dump all of the information. Okay. Once you have extracted that information, there's going to be a folder with the same name as the zip file. Okay, in this case, FlowAI version 2.3. Within that folder is the how-to instruction manual, as well as the all-important jar file. Okay, so again, you have to be very careful. Some of these plugins require R, and so you may want to read the how-to before you start installing the jar files. But the bottom line is you copy and paste this jar file and put it into your plugins folder. Okay, so if you are on a Mac, usually your plugins folder is directly underneath the applications directory. You'll see plugins, and then you can see I have a whole bunch of plugins listed here. Okay, if you're on a PC, you normally have to go to C:\program files / FlowJo v10 / plugins. Okay, and if you don't have the plugins folder there, you can create one and then just dump the jar file in that location. Okay, you should probably do that when you have FlowJo closed. So don't be adding or subtracting jar files with FlowJo open. If it is open, go ahead and do what you're going to do, but then quit out of FlowJo and then reopen it in order to get those plugins to work. Okay. All right, so Again, from FlowJo, that's going to be underneath the Workspace tab, Populations Band, Plugins drop-down menu, and click the top button, FlowJo Exchange, to get the plugins that you want. So I would highly recommend getting the Cluster Explorer. Phenograph is a really good one as well. FlowSum is a nice clustering tool. I'll show you all of these guys as we move through. But there's just a ton of them here, and I'm going to describe a handful of them that I think are probably the most useful for doing high dimensional analysis. Okay. The other thing I should mention is about high dimensional analysis. You know, this is kind of a loose term, but I generally imply that high parameter is 10 or more colors. If you have less than 10 colors in the experiment, odds are Tisney and the clustering tools are not really going to be super helpful to you, and it's probably going to slow you down more than anything else. Okay, but with 10 or more colors, this should be quite useful. Okay. So let's take a look at what we have here. Let me compress my workspace real quick. I've got only 4 files here, 2 that have been stemmed and 2 that have not been stemmed. But I've got a series of gates that have already been created, right? It's a bunch of cleanup gates, even have a dump channel here. And then, of course, I'm starting to look at antigen presenting cell compartments here. Okay, so starting at DR positive, we have a bunch of monocytes, dendritic cells, plasmacytoid dendritic cells, et cetera. Okay, and they have a number of cytokines that we can track their activation or expression of. Okay, so since we have the cleanup gates already in place, the next step is going to be to add some keyword information that tells us about these files. Okay, you may have some keywords already present that define what these things are, but if they do not exist, you want to go ahead and add them at this stage. So you would right-click on a file and then say, add keyword. And in my case, the first experimental variable that I would like to sort of make sure that I incorporate is the fact that these files are either stimulated or not. So I'm going to call the first keyword, I'm just going to call it something like the stim condition. Okay, so the first stim condition here for the first file, this one says that it is not stimulated. Okay, so no stim. I'm going to go ahead and assign numerical values to the different conditions. Okay, so anything that has the same condition is going to inherit the same numerical value. So in the first case here, sample number 1, non-stimulated, gets the value 1. The second sample, also non-stimulated, inherits the same value of 1. Okay, then those that have been stimulated with the toll-like receptor agonist, we're going to go ahead and give that the value 2. Right? And since the fourth sample here has also been stimulated with the same thing, we give it the same value. So my current setup here is 1122 for the keyword information. Now I also want to include a keyword that describes the different patients, right? I have 2 different patients here, right? Patient 1, patient 2. And so we're going to go ahead and incorporate that information as well. So what do? We right click and we say add keyword. And for this one, I'm going to call it, I don't know, patient number. Okay, and then for this guy, the first sample comes from patient number 1. So I enter the value 1. The second sample comes from patient number 2. So I enter the value 2. The third sample comes from patient number 1, so I enter the value 1, and then the fourth sample comes from patient number 2, so I'm going to go ahead and enter the value 2. Okay, now if there were any other conditions associated with this experiment, maybe the age of the patients, right, or the sex of the patients, I would want to include that information as well. If I add more files, right, that had different stimulations, right, maybe TNF or IL-1 or LPS or something like that, right, I would add that information in the stim condition column here as 3, 4, 5, 6, etc. Okay, now that I have the keyword information, it's time for me to figure out at what level in the hierarchy I want to begin my analysis. Okay. For me, since this is a fairly lower end high D experiment, right? We don't have 20 colors here. We've got about 13 or 14. I'm going to stick with a higher level in a higher level population. So for example, we'll just look at all of the antigen presenting cells. You guys, if you're interested only in monocytes or perhaps the non-classical monocytes, you could start at that level. It really depends on where you want to begin. But I want to take a look at everything that's alive in my tubes. So I'm going to go ahead and select the antigen presenting cell compartment. Okay, now from here, I have the option to use the plugin to downsample this. Instead of having 130,000 cells, I can reduce it down to some other number. Okay, I'm not going to use the plugin for this, but just to let you know, there is a plugin that allows you to do that, right? The downsample plugin here, and it just has a small prompt that asks you how many cells and if you want to name it. Okay, in my case, I'm actually going to use the concatenation window to handle this for me. So I'm not even going to bother downsampling at this stage. We'll use the concatenation window to do that. Okay, so let's pick the DR compartment from all of the samples. And the easiest or fastest way to do that is to highlight the DR compartment and then simply right-click on it. And then what you want to choose from here is the Select Equivalent Nodes option. And then what this does is it simply highlights all the other DR compartments in the other samples. Okay, so for the fourth sample, we've got 20,000 cells. Another one, we have only 28,000 cells. And then in the previous two, we have around 130,000. So I'm going to go ahead and decrease the numbers of cells, let's say down to, I don't know, let's make it 10,000 events from everybody. Okay, so now we want to go to the concatenation stage and do that downsampling. The way we do this is right-click on one of the selected DR compartments. And then what I would say here is go ahead and select the option that says Export Concatenate Populations. Okay, this brings up a little menu. It defaults to export. So you want to change this over to concatenate, right? We want to merge. We don't want to individually export the DR populations. Okay, make sure you know where this information or where the file is going to go. I'm going to dump it someplace on my desktop. Okay, and then in the include events box, this is where we can actually downsample. If you actually tick the box here that says include no more than, you can specify how many cells you want. So I want no more than 10,000 per DR compartment here per file. Okay, so it's going to take the DR compartment and it's going to take 10,000 events at random from that compartment. Okay, now what we want to do from here is expand the advanced options, maybe give this a name, U of A. In the parameters box, this is an interesting one. Today, we're going to use the all uncompensated parameters. And the reason that we're going to do that is because all of the samples have already been compensated. They have a compensation matrix that comes from the same day, the same exact day, the same exact panel. Okay. When we create our concatenated file, it's going to get dumped into this workspace. And I have a group already set up to capture the concatenated file when it comes in. When it comes in, it's going to automatically inherit the compensation matrix that's associated with these files. So everything will come in uncompensated, but then it'll pick up the compensation matrix and everything will be at that point compensated, okay? For most of the experiments, so if I was doing this for a longitudinal study or I've got lots of subjects where we're using, or we have different compensation matrices on the samples, right? One comes from, let's say, May of 2021, but I have previous samples that come from December 2020, right? And another one that comes from maybe June of 2020. All of those samples are going to have different compensation matrices on them. Maybe they're, the same panel, but they are taken on different days. So you want to preserve the compensation settings that you had on each of those files, in which case you want to use the second option here. Okay, but for me, mine is the exception to the rule today. We're going to use the top one that says all uncompensated because everything here is exactly the same. Okay, now down below where it says additional parameters, this is where we want to incorporate the keyword information that we added here, right? We had stim condition and patient number. So we go down to additional parameters, we say choose, and then from this box, we want to select the keywords that we added, right? So there's our stim condition and there's our patient number keywords that we added. Okay, and then you just click OK. The little menu will update and it'll tell you whether you picked up, 2 keywords. Sometimes it might even specify what those keywords are. Okay, and then now you can go ahead and concatenate the file. So you say concatenate, gives you another prompt. I like to dump this into the existing workspace. You can put it in a new one if you want, or you could do neither, in which case it just dumps the concatenated file into the folder that you specify and you can access it later. Okay, or you could do both if you want it. It's up to you. So we close out of this, then close out of that, and now we have a concatenated file, right? Concat U of A, and notice that it now has this compensation matrix associated with it, right? So all of my parameters in the parameter list here, I have both the uncompensated and then I have everything labeled comp, blah, blah, blah. Okay, so let me check the chat box. I see that there's a couple of things started in here. Can you reset the numbers to the maximum among samples? You could, but the problem there is, well, you can't. If you don't, so let me go back here. So if I have only 28,000 cells in this DR compartment from this sample, there's no way I can tell it to have 130,000 like the others, right? I can't make more, I can only make less. So when considering downsampling, a lot of times you just look at the sample that has the least numbers of events in it, and then you just downsample that to that particular file's number of events. So you don't want to set it to the maximum, you would set it to the minimum among samples. Okay, I meant maximum that allows between samples, not all events. Maximum between samples. I don't think I'm like, can you reset the numbers to the maximum among samples? Reset what numbers? The keyword values? So I'll have to get a specification on that. I'm not quite sure I understand the question there, Amir. So we may have to come back to it a little bit later, but I'm assuming maybe the keyword values here, you can always change these out, but you need to change them out before you concatenate, of course, because now they're written to the file. Okay, so now that you have your concatenated file, what I recommend people do is go ahead and gate these out first in terms of your categorical parameters, okay? So get your stim condition gated, get your patient number, any other experimental variable, right? You want to gate that first. So we go here, we'll start with the stim condition. And then what I recommend that you do here is this is going to be plotted on a bi-exponential scale. Just make it linear. And then I'd recommend that you look at it as a histogram, especially if you have lots of files. I would go this route because there's a nice little trick here. You can right click on the graph window and you can say create gates on peaks, right? Imagine you have 100 samples and you need to gate all the different categories, right? It's going to take you forever to draw gates right? 100 different rectangles or 100 different circles, whatever it may be, 100 different range gates on histograms takes a long time. So that create gates on peaks feature really speeds this up, okay? The one thing you have to watch out for is that sometimes that create gates on peaks doesn't always capture, you know, all the cells in it. So for example, I move the range gate a little bit here. Just check your workspace to make sure that you have the correct number of cells in that experimental condition. Okay, so in my case, I obviously should have 20,000 a piece, 50% a piece, right? So remember, the stim conditions represented TNF and non-stimulated, right? So the first sample here, I'm going to go ahead and rename it. The first sample labeled POP0, that is the non-stimulated, right, sample. And then the second one is the stim or the TLR stim, however you want to name it. Okay, and now I'm going to do the same thing for the patients, right? So I have another categorical keyword that helps me segregate the samples. And so patient number would be the next one I would go to. I'm going to do the same thing here. Notice that it's on a bi-exponential scale. Let's just convert it to linear. And then we make use of the right-click menu option here, create gates on peaks. Okay, check to make sure in the workspace that they have 20,000 apiece. And if you want, you can go ahead and rename them. Okay, I'm going to rename it just PT1, right? Patient 1 and PT2. Rather than POP1, POP0. And this is patient 2. Once you have your categorical gates set up, right, you can drag and drop different conditions to each to get any kind of comparison that you want. So I can say, okay, well, I want to look at my patient 1's non-stim and stim conditions. So you can simply drag and drop gates under there. And let's do the same thing for patient number 2, right? So that we have every possible combination in the experiments kind of already set up. You don't have to do it. I like to do it just to make sure that, you know, I have everything kind of mapped out before I begin my t-SNE and making comparisons, okay? Especially after, I like to do this before we run clustering algorithms, because clustering algorithms spit out lots and lots of populations, and these things can kind of get lost in the hierarchy. So set it up first, and then you don't have to really worry about it so much later. Okay, so now what we're going to do is a round of dimension reduction. So again, I mentioned that I like t-SNE. t-SNE's a lot faster than it used to be, and again, it gives you that nice granular sort of set of islands. So we'll go ahead and run t-SNE first, and if we have some time, we'll go ahead and run UMAP as well, so you can see what the difference looks like here. Okay. Now, for running t-SNE or any dimension reduction or clustering algorithm, you want to make sure that when you run the algorithm that you don't give it parameters or fluorochromes that you've sort of already eliminated from the analysis, right? So we know that we're looking at the DR compartment here, right? All the antigen presenting cells. So we already cleaned up the data. We don't need the viability dye to, you know, to figure into the t-SNE equation. So let's go ahead and dump that from it altogether. The other one that we don't need here is PE-Cy7, because this is our dump channel, right? We had gotten rid of all the T cells and B cells, et cetera. So we don't need t-SNE to crunch numbers over that fluorochrome either. Okay, the remaining fluorochromes you probably want to keep in, right? Lineage markers as well as some cytokines involved, right? Especially that anything that has to do with the antigen presenting cell compartment, we're probably going to keep in. Okay, now for the latter section here, there's a couple of options, right? The learning configuration, you can choose this opt-SNE. I highly recommend it because this one has modified the algorithm such that it identifies groups of cells. Once it has identified groups of cells, like the resolution gets to a particular point where it's fairly clear that you're not going to increase resolution by adding more iterations, the algorithm essentially stops. So using this greatly increases the speed with which t-SNE will complete. If you don't use this, then you rely heavily on these three knobs that are down below, primarily the number of iterations. So if you had this on manual and then you specify 1,000 iterations, then t-SNE will actually go through each of those 1,000 iterations or 1,000 cycles before it finishes, whether or not it needs those 1,000 iterations or not. Okay. The OpsNE takes care of the number of iterations here by monitoring the density of the clusters that you get, and essentially how many there are based on based on the perplexity or sort of the K value here that you specify. Okay, so the perplexity, you can think of this as a K value, or the number of cells that the algorithm has to count in order to sort of be inclusive of what is called a neighborhood. But a lot of times I just liken this to the amount of white space that is between islands. You can play around with this number. If you find that your t-SNE plot doesn't have a lot of white space, you can kind of increase the perplexity to try to separate those islands out. But it, again, it just requires a little bit of playing with. The learning rate is essentially, again, the speed at which the algorithm is going to progress, and kind of how, I guess, I don't know how best to put this, but it's how nicely it sort of allocates cells to a given neighborhood. You get more, I would say you get nicer, rounder populations with a lower learning rate, right? Meaning the algorithm progresses slower, but that's the opportunity cost, right? You get a really nice island, but it takes t-SNE a little bit longer to produce the output, right? If you can afford to be a little bit on the more crude side, you can increase the learning rate so that t-SNE finishes a lot faster. And again, these three things to some extent are handled by the OpsNE algorithm. So I wouldn't put too much emphasis on this unless you're running millions of events, in which case you may want to bump up the the iterations here to something like 3,000, and then you'll have to kind of play around with the other two after you get the initial image. Okay. Then you can choose here the so-called KNN algorithm, the K nearest neighbors algorithm. So there's two different types here. If you want to go the super fast method, you can use the approximate or this ANOI method. This method is what Spotify uses to figure out what the next song in your playlist ought to be. So if you like Spotify and how it chooses music for you, you may want to stick with the approximate. This is a bit faster than the Vantage Point tree. Okay, in both scenarios, both are published. It's up to you which one you would rather use. And then the gradient algorithm, the default gradient algorithm is the original one, which is Barnes-Hutt. But there's another version called the fast Fourier transformation, or the fast Fourier interpolation, FITSNE. So the super fast way of getting t-SNE done would be to have this configuration: auto OpsNE, approximate, and FFT. Okay. In our case, we don't have a real big file, so we can kind of wait around for it to finish here. And this will give me enough time to kind of go through the question box as well. Okay. And while this is going, I'll take a look at the chat box to see if you guys have any other questions. Okay, so back to the original question about the maximum number. So like when you have a few samples with different counts, such as 100,000, 20,000, 30,000, if you want the maximum counts between them, which is 20,000 in this case, to be chosen, is that called minimum? Yeah, well, to me, it's the minimum, it's the most limiting sample, right? If you have a sample that has 100,000 cells, another one that has 20,000 cells, and another one that has 30,000, the one that only has 20,000 cells is the most limiting, right? It's the minimum, sort of the minimum sample. And that's the one that you would go with for downsampling, right? So it's just exactly what happened in my case here, right? My DR compartment is most limiting in I think it's the fourth sample here, right? I only have 21,000 events. So I would choose this sample and I'd say, okay, well, if I want to do 20,000 events or somewhere in that ballpark, I'd say, okay, well, I have to adhere to this guy's maximum number, which is 21,369. So I guess I see what you mean. It's the maximum number of cells on the minimum or the most limiting sample. So it's just, I think we're two ships passing in the night. I'm not explaining it well, so I apologize. But yeah, whichever sample is most limiting, that's essentially what you want to go with. Okay, I see that our t-SNE popped up while I was talking. So there you go, right? t-SNE produces this kind of an output. We discussed that earlier. Now the question becomes, well, what the heck are those islands? You can actually make use of a very quick tool here to kind of help guide you or orient you on that t-SNE plot. So what you do is you just drag in your concatenated file into the workspace. And let me get rid of the page breaks here. And there's a very nice tool. When you right click on the plot, you go down to the bottom where it says make multigraph overlays. And there's this option that says multigraph color mapping. Okay, and this will create, right, a series of heat mapped t-SNE plots for you. Now, again, we probably don't want to look at the dump channel or the viability die, but everything else is probably interesting. And this will take a second or two, and there you go, you get your panel. This is usually a figure, right, in a paper. You always, or at least when t-SNE first came out, you used to see a figure like this all the time, where they would have, you know, essentially all the different markers heat mapped on here. Obviously everything here is DR positive, right? But if you want to get an idea of where your monocytic cells lie, you kind of have an idea now that it's kind of on the, I guess, the eastern portion of the plot, right? East and south. Your TNF expressors are over here and over here, right? Just a general way to get you oriented on the t-SNE plot. Okay, now what you normally want to do though is after orienting yourself is you want to figure out what the difference between your non-stimulated and your stim are, or maybe your patient 1 and patient 2, or perhaps your non-stim from patient 1 and your non-stim from patient 2. Right, so if we just want to compare non-stim versus stim, we can just drag those in, right? So I take my non-stim gate, dump it into the layout editor, and take my stim gate and do the same thing, overlay them. And then I'm going to go to the edit tab and just get rid of the page breaks here. And we obviously want to convert this, we don't want it as a histogram. Okay, I recommend that when you look at t-SNE plots that are overlaid, the best option here, I think, is a contour plot with outliers being shown. And then, of course, we have to specify the axes, right? So t-SNE 1 and t-SNE 2. Okay, and then click OK. Okay, so there we get our nice little plot. The stim condition is in blue, the non-stim is in red. Okay, you can clearly see that there are islands or groups of cells, right? Pockets of cells here that are distinctly associated with the stim condition, but not with the non-stim, and vice versa, right? We have a lot of cells here in the red that are only existing in the non-stimulated condition. They don't exist when you add toll-like receptor agonist to them, right? The odds are, or what is happening here, right, is your non-stimulated cells, when you dump the toll-like receptor agonist on it, we get a bunch of angry, you know, antigen-presenting cells. They start producing a lot of different types of cytokine, and that's essentially what you see here. These different islands are most likely cytokine-expressing cells of different lineages in the antigen-presenting cell compartment, right? But how cool is this? You can see the stark contrast, right? The differences between the two right away. There are cells that are obviously both conditions have in common here, where there is overlap between the blue and the red, but there are clearly phenotypes that are distinct to one condition or the other. And so This to me is why UMAP, why TISNE, why TriMap are particularly powerful, and that they show you these differences right up front, right? So it's really quite useful that way. Now, it's good that we know that there are differences between these samples, but we probably want to dig a bit deeper and say, well, what the heck are these phenotypes, right? What are these clusters that I see on the TISNE plot? Okay, let's assume for a second that you're interested in the stim condition and you want to identify the phenotypes here that are different, between, let's say, the blue and the red. So we go ahead and find our stim sample if that's the one we're interested in. And I highly recommend you convert this over to a TISNE plot that looks like the TISNE plot that you have in the layout editor, right? So we do TISNE 1, TISNE 2, but also convert this over to a contour plot as well, so that when you create your gates, a little bit easier to kind of see. Okay, so we come here. All right, so let's say that I'm interested in, I don't know, this little island down here that's kind of nicely separated away from everything else, right? So that's this guy over here. So we kind of take our polygon tool. I'm going to use the contour lines to kind of make a judgment call about where the boundary between the different phenotypes happens to be. And I'm going to refer to this as my query. Okay, now from here, you have a query gate or a gate that is looking at those phenotypes. You just take that query gate and you overlay it with your TISNE plot. Right now, I would recommend that you come in here and you change this to a highly contrasting color so that you can see it against the white space here. Okay, but we right click on the plot. We say make multigraph overlays. And I would say use this option that says histograms. Okay, and then we can stretch this out a little bit. Now you'll notice that in this little panel, there's a bunch of fluorochromes and other things in here that aren't particularly useful, right? So I don't really need the sample ID or the fact that I have BUV 496, right, which is uncompensated. What do I want to look at that for? So I recommend that you right click on this panel, go down to the very bottom where it says select multiple. And this will give you a nice little pane that you can use to customize what you want to see. Okay, so let's dump viability, of course, and the dump channel and trim this list so that what we're looking at is actually relevant to the study that we're doing. Okay, so here we go. Let's stretch this out just a little bit more so that I don't know how big the computers are on your end, but I know a lot of people use these laptops that have the absolute smallest screens, and they may be high resolution, but heck, man, you need a magnifying glass in order to see what's going on them. Okay, so here we go. Stretch it out a bit so you can see what's going on. This little island, right, is the dark blue trace. The light blue and the red correspond to essentially the stim or the non-stim condition. So this little segment, right, that happens to occur in the stimulated sample is definitely expressing IL-6, right? Whatever these cells are, pro-inflammatory, IL-6 present, right? Obviously, they are DR positive. That's not super informative, but there is a gradient of expression of MHC there, so it may be important later on. Okay, now in this case, we look at this lineage marker here, CD1C, and you can kind of see there's sort of this, I don't know, bimodal distribution. You got a lot of negative, you have some that may be positive over here, but there's no real good distinction between the two. So it's hard to say whether or not these are true dendritic cells or not, because it looks like you've got a mix, right? Some that have CD1C and others that do not. So we'll talk about this parameter here in a little bit. Okay, they definitely express TNF. Mature 83 is present. Oh, these guys, for the most part, well, maybe, again, if they're monocytic, right, CD14, they're most likely not CD1C dendritic cells, right? So probably monocytes expressing a lot of different cytokine here. IL-1 is present, IL-12 is present. They are not the patrolling monocytes. And of course, they are not plasmacytoid dendritic cells either. Okay, so probably the bulk of these guys are monocytic CD14 classical monocytes. Okay, now I could take this information, right? I can go over here. I could say, okay, well, that's great. I've identified this guy. I might rename my query gate, I don't know, IL-6 TNF expressing CD14 T or CD14 monocytic cells. Right? I could rename it and then create another gate to figure out what the other populations are. Okay, but again, if I'm just kind of orienting myself around the plot, I can just move the gate over, right? And then that's going to change the trace here. And you may want to, I don't know, you may want to hone the gate a little bit to kind of, get a little bit narrower of a sample and just see how these phenotypes change, right? Another IL-6 expressor, but this guy looks to be more heavily CD1C positive. Some negatives over here, but it looks like this is probably looking more like a dendritic cell. TNF is present, 83 is present. Okay, and these guys, for the most part, are CD14 negative. Also have some IL-1 in there. IL-12 is present in some, but not all, right? And you see that you have kind of a, well, I guess it's positive for all, but there's kind of a wide gradient here. Okay, now with some of these fuzzy parameters, right, the reason that we don't get good separation here, a lot of times that may be due to our original transformation settings in the original file. So for example, if I come here and I take a look at, let's see what we have defined as CD1C positive cells, right? So let's take this up a notch and just take a look at the gate and how the cells look in the original sample. Okay, CD1C is one of those smeared markers that's very difficult to kind of, see what's truly positive away from what is negative, right? This is what we're calling negative, and this is what we're saying is positive. You can see here there's no good white space. We don't have a huge order of magnitude difference between the two, right? If anything, there's maybe half a mag, right? Half an order of magnitude difference, which is not fantastic. Okay, for these algorithms, it would be better to come in and look at your, separation here between your positive and negative, and try to maximize the distance between these cells. So you may want to come in, and this is what I would normally do if I'm doing this for a study of some kind. I'm going to go ahead and transform that CD1C fluorochrome so that I can stretch it out, maximize this distance between negative and positive as much as possible, and maybe even compress the negative so that it's super obvious what the negative population happens to be, right? Versus the true positive. Now, unfortunately, we're going to kind of run into a little bit of problem here where we can't get, I don't know, it's not going to be a great display. I want to maximize this white space, right? But not to the detriment of decreasing the distance between positive and negative. So in some cases, all you can really do here is stretch this out and kind of hope for the best, right? So maybe add a little tick there. And odds are the algorithm is actually going to be able to pull this apart, no problem, and probably lump the other half, let's say, these guys over here into this same population. But you kind of have to test it and give it a run. But some markers, unfortunately, are going to take you more time to kind of tease apart what's going on, and CD1C is no surprise that way. Okay, CD14, same thing, it's a smeared marker, so maximizing the distance before you run t-SNE and the algorithms is going to help the algorithm to really segregate those two populations. Okay, so that's the use of t-SNE. You can do more complicated things, as I mentioned, but once you have your, categorical parameters set up, right, you can do any kind of combination that you want. So again, if you want to just say, okay, I want to look at the stim from patient 2 and I want to look at the stim from patient 1 and see if there's any differences between these guys. Now you can do that very easily. Just drag the two in, And you're going to convert this again over to a t-SNE plot. So let's make it a contour and scroll down here, say t-SNE 2, show the outliers, and then click OK. Okay, now in this case, right, we're looking at the stim condition that come from two different patients. So we kind of expect that they should have the same types of cells present, right, if they're a healthy patient, but the quantities are going to be, going to be different. So in some locations, you may see that there's more, for example, whatever these cells happen to be, there's more of them in the blue patient versus the red patient. There are some cells that the expression levels that are present probably for certain markers are significant enough that they look like unique islands, right? So this little island down here, most likely the same type of cell that's over here in the red patient. But again, it takes a little bit of gating, comparing the two to figure out whether or not that is the case. But I would assume here that these are healthy patients. They've just had LPS dumped onto their blood cells, and they're essentially going to generate the same types of cells. Okay, so obviously the larger the cohort, the easier it will be to figure out whether or not this island is a specific island, and that maybe there's something unique about this patient versus all the others. Okay, so we can combine this now with clustering algorithms. So we've been doing, just overlaying the different categorical conditions or categorical gates on top of one another. But if you want the algorithms to do the work for you, you can kind of come in here and you can say, okay, well, I've done t-SNE. Now let's just see what FlowSum or phenograph or XShift will do to the, to the data. What populations do these algorithms see? Now, again, for us, I'm going to use an algorithm called XShift because it's quite fast, and so it's great for tutorials. But the general idea is, the general idea here is going to be the same whether I'm doing this for phenograph or for XShift or for FlowSum, right? You're just basically picking on a series of fluorochromes or parameters that you want the algorithm to crunch the data over. Okay, and then from there, you have some choices that you can make. You can specify the number of next nearest neighbors. Okay, so when it comes to a clustering algorithm and the K value that you choose here, the larger the number of cells that you choose for the nearest neighbors, the fewer amounts of populations you're going to get spit out from the algorithm. So if you feel that the algorithm is not identifying your nitty-gritty phenotype that you're looking for, come back into it and reduce the numbers of nearest neighbors. So in my case here, let's say I've got, 20 different phenotypes. I know just from experience that setting this at 102, which it kind of defaults to, is probably a little bit high. It doesn't give me enough clusters to really identify all the different phenotypes. If I divide this by 3, it generally tends to work a little bit better. I like my K values around 30 anyway for most clustering algorithms. So we'll go ahead and reduce this down to 30, and that's going to give me more clusters, right? More phenotypes here in the end. Now, the downside to over clustering or creating multiple clusters is that a lot of them are actually going to divide up a single population of cells, that you're going to break it up into smaller and smaller parts, right? When indeed they're really just one phenotype. So the downside here is you've got to do a little bit of investigative gating to figure out which clusters are the same, and maybe you can Boolean them together after the fact. But it's better than choosing a K value that's too high, in which case you will not see the rare population or the population that you're after. So I always tell people to try to be on the more liberal side here, get more, it's better to over cluster than to under cluster. Okay, the distance metric, Nikolai Samusic is the one who published this algorithm. So he recommends that you use angular distance to measure populations in high dimensional space. A lot of other algorithms use Euclidean distance, so you have the option here to use either. I'm going to stick with his recommendation, which is angular. And then the subsampling limit, this is only really useful if you have millions of events. You can, again, you can kind of do a subsampling here so that it doesn't go through all of the cells that you have in the data set to come up with a series of phenotypes. It'll put all of the cells into those phenotypes, but it doesn't need to use all of them in order to calculate that space. Okay? And then the run ID, if you're going to run this multiple times, it's just going to automatically generate a run ID for you, which is pretty much what we want. Okay, so as I mentioned, XShift's pretty fast, so that's why I'm choosing it for this tutorial. It's not necessarily the one that would necessarily work best with the types of cells that you have. So again, you kind of have to test these algorithms in your hands to figure out which ones do a better job of mapping back to your, your cells of interest. But in any case, there are some tools to help you do that as well. And I'll show you the Cluster Explorer here in a moment. Okay, so if with XShift, let's say I found 34 clusters, right? That's great. I could come and then run another algorithm on top of that if I wanted to compare this maybe to FlowSum or to Phenograph. I come into FlowSum's menu, for example, and I can say here, make sure that you generate 34 clusters just like XShift did. Okay, so FlowSum has this box that allows you to specify how many clusters you want. I kind of like XShift and Phenograph in that they don't ask you how many clusters, they just kind of they ask you, well, how many cells do you think I should incorporate into an initial cluster to assume that that's a population of cells, and that's what that k nearest neighbors value essentially is. So this one, you have to kind of upfront specify how many you think are there. And to me, this is a hard number to come up with unless you've run another algorithm on the data set, okay? There are a bunch of other knobs here that I'll kind of describe maybe a little bit later. They're not really important for our work that we're going to do, but FlowSum is another fast clustering algorithm, so it helps me with tutorials because I can quickly show you the outputs and then how you would work with these outputs in the FlowJo workspace. Personally, when I am doing analysis for rare cells, or let's say, I don't know, most immunological data sets, for whatever reason, I like Phenograph the best because to me, it tends to recapitulate my manual gates a little bit better than the other two algorithms, but I find that that's data set specific, right? So XShift does a really good job with CyTOF data, and Phenograph does a great job with flow cytometric data. FlowSum does a good job too, but so far I just haven't gotten quite as good results matching these back to manual gates as I have with Phenograph. Okay. So again, it's a matter of testing and what your personal choice is, but if I was to hit it, I would say try Phenograph first and then try the other two. Okay, so now we have these clustering results, right? We've got a bunch of phenotypes that have been spit out, POP1, POP2, all the way to POP34. We don't have any idea, though, of what the phenotypes of these clusters are. So for that purpose, we're going to make use of another plugin called the Cluster Explorer. Okay, this will help you identify what the phenotypes of those clusters are. Okay, so you come here, Cluster Explorer. It's a really cool tool. You do not need R in order to run this, so it's fantastic for that purpose. Okay, again, you just tell it which fluorochromes you want it to generate the interfaces for, and then it'll go ahead and do it. Okay, so it has a series of windows, and I probably should start with the control panel window so you kind of know what's going on here. But the global node is just referring to which population you're looking at in the workspace. So we're looking at the fully concatenated file here rather than a gated population. And of course, all 40,000 events. So you can subsample here too if you want, to some lower event number. But in general, we probably are going to leave that alone. Okay, but it's useful if you have a gating hierarchy and maybe you want to drop down to, you want to drop down to some level and observe what the clusters look like at a particular level. Now, keep in mind this concatenated file, we are looking at the entire antigen presenting cell compartment. So we're looking at the DR positives. We don't have any dead cells. We don't have any debris or anything else in there. Okay, and of course, you can choose between your FlowSum clustering and your X-shift clustering at the cluster set button. Okay, I'll explain the compare to a little bit later. The profile plotting gates, right? So that's referring to this plot right here. This is referred to as a profile plot. And you can gate here, right? So you can actually say, well, I'm really interested in looking at TNF, my clusters that express TNF. So maybe I want to look at my high expressors first. So you can just go ahead and create a gate on that, right? And it'll go ahead and isolate the clusters that express high levels of TNF. You can see which cluster numbers these are in the plot right next door. Right, so this is cluster 10, cluster 15, cluster 18, it looks like, and cluster 24 and cluster 27 that I have isolated here, right? 5 different clusters. It also sort of back highlights them on the, on the heat map here. And it's nice because it has a cluster number next to it. So only the highlighted rows are corresponding to the clusters that you have here. And so you can inspect whether or not they differ in any way. In this case, it looks like the primary difference between these clusters, they all express TNF, but they differ in terms of their IL-12 expression and, of course, on their CD83, the level of CD83 expression. Okay, looks like CD1C is also a factor here. So whether or not you are looking at dendritic cells. Okay. But you can combine logic here. So the default is to be AND. So you could say, all right, well, I want to look at all of my TNF expressors and any of those that are also my monocytic cells, right, that are also expressing high levels of CD14. Okay, so you can combine the two Boolean logic, and that essentially gives you that, that output. Now you can clear this. And you can say, okay, well, I want, I don't know, I want all TNFs, but now you say you want not those that are CD14, right? And in this case, it's just going to show you the non-monocytic, right, TNF expressors. So these guys, in theory, should be probably your CD1C high, but you've got a population here that's CD1C negative, one that's high. And then my guess is the other one's going to be, yeah, well, CD16, it's just, maybe there's just not a lineage marker here to define what that cell is. It's not plasmacytoid either. So we don't have any other lineage marker to help us decide what that cell is. But interesting, okay? So we've got lineage negative, but expresses quite a bit of cytokine here, at least TNF. And it looks like it expresses a lot of IL-1 and a lot of IL-12 as well. Okay, but in any case, this is what that profile plot gates does. Okay, you can switch here between plotting the medians or the means, right? So we'll kind of change the graph a bit. And then you can use something called scale values or channel values. The scale values are what you see when you look at plots in FlowJo or looking at this t-SNE plot here. This is what you actually witness is something called scale value, right? The channel value is more like the raw data. So this, even though it doesn't have a huge impact on the scaling of the data here, you have the option to look at either one. Okay, as far as the 2D plots are concerned, you start with one 2D plot down here, but you can add more by clicking that button. And then this will allow you to, if you select those high TNF expressors, whoops, we don't want not logic, we want AND logic. So let me put AND back on. Let's say again, we want to look at all our high TNF expressors. You can come here and you can see what the context of these populations look like, right, across any other 2x2 plot. You don't need to look at them only in Tisney, axes. You can come here and you can change this to anything else, right? So you can kind of see here the distribution of these clusters across your dendritic cell populations. You can add more of these 2D plots to kind of stretch this out even further. So you can look in multiple panels, basically, kind of look back on what those things are. Okay, if you say play clusters, all this does is go through each cluster kind of one by one, and so many clusters per second. And of course, you can stop this, etc. Now, pretty fancy tool, right? Has a lot of useful information. I will point you guys again to the fact that these clustering algorithms, right? I just did want to point out that you see all these mid-expressors, right? These are kind of unusual in my eyes. I don't normally gate mid-expressing TNF, or mid-expressing populations, but these algorithms have a unique ability to pull these guys out fairly nicely. Look at that. It's done the same thing in a lot of mid-expressors here for IL-12. So it's not unique to TNF, right? And maybe CD83 is kind of all over the place as well. I would have expected a little bit more with CD14, but this is more or less on-off. But in any case, I just wanted to point out the power of these algorithms to you in that, right, they can pull stuff out that is a little bit unusual. Now, if you find that this is really cool, I will tell you the really powerful thing about this, if you're going to use clustering algorithms, is make use of the heat map down below. The heat map, let's go ahead and clear stuff here. The heat map, you can modify this table to include your conditions, right? So again, you've got your experimental conditions here, non-stim, stim, patient 1, patient 2, etc. You can really get into the who is doing what type of thing. The only downside to this Cluster Explorer is the fact that the windows kind of go, it's hard to kind of bring them into the forefront. We need like a PowerPoint tool that says bring to front, right? Bring all to front so that you can bury the FlowJo workspace again. But in any case, you come here to the heat map, go to the menu option, and come here where it says add nodes as columns, right? You click on this, and now you can tell it, okay, well, now I want to see what the skewing is between non-stim and stim. Are any of these clusters more heavily associated with the non-stim condition or the stim condition? So you say select new columns, it goes ahead and add them here, and it heat maps them differently than they heat map the fluorochromes. So you can easily tell the difference between the two tables, essentially, right? So when I'm looking at this heat map, right, the non-stim condition is on the left. The stuff that's in yellow means that there are more cells, right, in this particular cluster. This happens to be cluster number 1, right? 3,000 events, 99.5 of those, 99.5% of those events, right, come from the non-stimulated condition. The stim condition, on the other hand, contributes almost nothing to this, okay? So this cluster number 1, more heavily skewed, right, towards the non-stimulated condition, okay? In contrast, right, you have clusters like 9, 10, and heck, a whole lot of them here in the middle span that are more heavily skewed towards the stim condition, okay? So in my opinion, like if you're just looking at lots and lots of data, you can add these columns here, your experimental condition columns, and you can quickly pull out clusters that are relevant to the condition that you're looking for. And then, you would run this again and see which clusters are consistent. Do I constantly find that I get this type of a phenotype in my stimulation condition? Maybe it's a phenotype I've never seen before, right? In this case, it's a IL-1 expressing monocyte, mid-level expression for TNF, right? Maybe in the past, all I've ever seen is really high expression of TNF, right? Maybe modest expression of CD14, high expression of IL-1, et cetera, right? But this time, I run this experiment multiple times and I keep seeing this cluster pop up, right? This one that constantly seems to have this sort of mid-level TNF expression. Okay, this tool, you'll see that this, whether or not this occurs and then to which condition it occurs most in. Now you can do, again, you can extend this, so you can add some more columns here, and you can say, okay, well, I really want to compare the stim condition of patient 1 and the stim condition of patient 2, right? Is there anything here that would grab my eye that's different between these two patients in terms of how they respond to the stimulus? Okay, for the most part, again, these patients, the clusters are essentially evenly divided amongst the two, with a slight difference here maybe on cluster number 7, right? There's only 6 cells here, and in the case of the patient number 1, well, whoops, I didn't expand this fully. Not looking at the full gate. So what I should do here is probably reset the table. So that's a bad example. Let me quit this Cluster Explorer and just reopen it under those 2 conditions, because I saw that I couldn't expand that table quite all the way that I wanted to. So we're going to go again here and just say Cluster Explorer and try to add those 2 without the others so that it doesn't clutter that table too much. So it may just be that if you try to add multiple things onto this table, it's not very clear after the second addition, but on the first add, you should be okay. So let's say we want to look at, again, stim of patient 1 and stim of patient 2. It's not picking up that node. All right, so there seems to be like a nice little, it's a bug that I don't really like, but in any case, what I was trying to show you guys was the skewness of patient number 1's stim versus patient 2's stim, but this guy doesn't seem to like, maybe I can't add 2 of them at a time. Maybe that's it, I don't know. Let's try this again. Add nodes as columns, choose a second one. Okay, so you have to do it one at a time. Sorry about that. It works fine for the parent level nodes, but any child node, you have to do it a little bit differently. Okay, so what I'm looking for here are differences between patient number 1's stim condition and patient number 2's stim condition. And if I run down through this, the pattern looks pretty much the same from sample to sample. Now you'll notice that when I hover over each of these, right, this menu down below can kind of change. So there are values in each of these cells. So if you actually maybe want to take a look at the exact events rather than the heat map, you can copy the content here over to to an Excel table or maybe Prism or something like that. Okay, but the bottom line is this heat map is supposed to help you with the skewness of those clusters towards your experimental conditions. So I apologize for the poor example there, but all it requires is that you add them kind of one by one rather than simultaneously, as you can see here. It kind of caused this dual representation of the first patient. Okay, so I would say that's Cluster Explorer. There's one last thing in the Cluster Explorer. If you want to compare clustering algorithms to one another, there's this compare to button here. So you have to have run at least one other clustering algorithm. And what this does is it sets up a table that has a series of scores here that tell you whether, the mutual events that are shared between the clusters. So for example, here, the X-shift cluster number 21 and FlowSum cluster number 24 are probably most similar to one another. They have 133 events that they share between the two. So they're essentially trying to define that same, same population. So all that stuff that's kind of outlined with the red boxes, those are going to be the clusters that are most similar to one another, and the ones that are empty out here. There really isn't much overlap between those clustering algorithms, and so that you don't see any cells kind of allocated for them. So, for example, if you were to look here at cluster number 28 for X shift, there's no real good corresponding cluster to flow sum, but the algorithm says, well, even though they don't share mutual events, you could say at least maybe somehow in multidimensional space they're getting near one another. So flow sum cluster 31, it looks like, would be most similar to X shift's cluster 28. Okay, it does a good job for the first few here, but then it kind of degrades over as you get further away. And that kind of makes sense. I mean, every algorithm looks at the data differently. You can kind of swap here between the Jacquard index versus mutual events versus something called the F measure. I don't know the difference between the Jacquard index and the F measure, so I apologize for my lack of knowledge there. The F measure essentially is looking at something called precision and recall. So instead of just mutual events, the F measure looks at not only the events that should be mutual, but also the events that should not be there. So it's a combination of both the mutual events and the ones that ought to be excluded from it. So you don't want to have cells in there that don't belong. So the higher an F measure means the more perfect it is, right? In this case, 86% or 0.86, right? It means that we've got a lot of the same mutual events, as well as we're kicking out cells that don't belong in these clusters. So 21 and 24, these guys are very close to one another, but clusters down here that have a score of 0.3, et cetera, these are going to be pretty bad. And I think the Jacquard index kind of follows a similar measurement. It's calculated differently. So I have to kind of dig into the Jacquard index to figure out what that actually is calculating. Okay, but in any case, that is a tool that's available to you as well. All right, now again, I mentioned that maybe that cluster number 9, from X shift, that was that mid TNF expressor. It was really, let's say kind of unique, but you had picked it up in multiple experiments. You might ask yourself the question, well, hey, I want to do a follow-up experiment on that cluster. Like, I keep seeing these cells. How can I manually gate those cells, right? The algorithm pulls it out just fine, but how the heck am I going to get it if I wanted to manually gate those samples? Okay, so if you want to convert stuff from an algorithmic method to manual gates, the tool that we recommend that you use here is something called the hyperfinder. And you have to, obviously, I always make this mistake, but you have to choose the root file and then you use the hyperfinder. Okay, and then from here, you tell it which fluorochromes you have available to use to isolate this cluster. Again, assuming that you have a viability die and the dump channel is already taken care of. You select those parameters. There are several other settings here. The maximum number of gates. So if you're going to do sorting, obviously, you probably only have a maximum of, say, 4 or 6 gates available. So you can kind of reduce this if you know that you're going to go to a sorter. But obviously, the more numbers of gates that you have, the better the algorithm will work. The F measure, the higher this value is, essentially it's telling you whether or not you want do you want higher purity or do you want higher yield? So increasing this value increases the purity, decreasing it essentially increases the yield. So if you want more cells, decrease this. You want higher purity, increase that value. Okay, and then as far as the validation set size and the downsampling limit, again, the downsampling limit, if you've got millions of events, you don't need hyperfinder to try to create gates on 2 million cells, right? You just kind of need the optimal setting for the, that gives the algorithm enough density so that it can make a distinction between cells that belong and cells that don't belong. So some subsampling limit, usually you know, 10% of whatever you're using tends to be all right. Although I haven't tested this in my hands to go, let's say, over 5 million events. So you may need to play around with the amount that you downsample if you guys are doing large numbers of cells. Okay, and then the validation set size, this is always about 30% the size of whatever you include here. So if you have 40,000 cells set here, the validation set is another group of cells basically that the algorithm uses to kind of test against to figure out whether or not it should include or exclude cells in when it creates its gates. The higher this value is going to be, the slower the algorithm works. But again, you're probably going to get a higher purity if you increase this. Okay, so we'll go ahead and click with the defaults here. It's going to give me 8 gates. You get this little window again asking you which cluster or which population you want defined by the hyperfinder, and we can say, okay, well, I want cluster number 8. Whoops, I think it was actually cluster number 9, right? That was the one that was interesting. Not that it matters, but go ahead and click OK, and then it's going to bring up this window here. And it sort of goes through several iterations to kind of hone these gates, again, using that validation set to try and, you know, tighten up the gates. And again, because these are algorithmically defined populations, the gate series may look kind of strange, right? So your first gate here is going to be CD1C versus TNF, right? Then you're going to have 1C versus 14. Then you're going to have, get this, right? IL-6 versus IL-12. That's totally weird. And then you'll have, in this case here, IL-6 versus CD1, right? 83 versus IL-1. I just love the cytokine by cytokine gates. But in any case, you get these set of gates, right, set up for you in that window. And then it actually spits them out for you here in the workspace. So here's all your hi-fi, blah, 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 and it tells you which cluster essentially you were going after. X shift cluster number 9, right? And then you can open this up in the layout editor and you can say, okay, I just want to visualize, this hierarchy. You can go ahead and just use the ancestry function here, right, to see those gates in case that you close that window, which I always do, and I forget that it's there. Okay, but you get your little ancestry here so you can see the series of gates that you need. If you were to manually gate cluster number 9, this is essentially what you would do. Really wonky looking initial gate, right, between CD1 and TNF, so on and so forth as you go through the list. Okay, and of course, this information, any gates that you have in FlowJo, you can export to Diva if you'd like, right? So you can say export to FACS-Diva. If you have an existing Diva experiment, you can modify it. You just tell it which gates you want, click export to Diva, and then we'll go ahead and modify that experiment for you. Okay. There's some other tools here that might be of use to you guys. I really like the violin box plots. You know, this one will give you a nice set of figures for papers as well. So especially if you're working with a series of clusters, or maybe you really like the clustering algorithm output that you get from XShift or FlowSum, right? You can go ahead and say, okay, well, I want to violin box plot all those populations and then just see what their you know, what their expression levels across all these different markers look like. Now, granted, we already did that in the Cluster Explorer, but this is just another way of displaying that information, right? So it'll come in here and it'll open up a web page, and then the so-called rain clouds here are actually the violin plots, but that just takes data that exists in your workspace and essentially dumps it here into this web page. And you can kind of see what data are included if you click on the data tab. You can get rid of some of the parameters if this was too many, right? Maybe you don't want to look at all of the fluorochromes, or perhaps you don't want to look at all 30 clusters. You can go ahead and hone what you see here in the data tab. And then in the rain clouds tab, this is obviously where you get your right, where you get your nice little violin plots. Okay, you can change the theme and that kind of stuff. There's some other things that you can see in here. Correlation plots, I think, are really useful, especially when you're doing large studies. You have multiple different conditions. So let me refresh this guy. Hopefully it doesn't take too long, but this allows you to see which cytokines or which lineages are sort of correlated or anti-correlated to one another. Right, so the heat map that's giving you here, I think the more orange the colors are, the more highly related, or the higher they are, more highly correlated they are with one another. So DR and IL-6, obviously, if we're looking at a stem sample, DR and IL-6 apparently correlate really well with one another, but it looks like IL-10, for example, and IL-6, right? One is immunosuppressive, whereas the other one is pro-inflammatory. These guys have a very cool color, so they're anti-correlated with one another, and that kind of makes sense, right? Because of the nature of the algorithm. Okay, so in any case, there's a bunch of visualizations that are here that I think kind of useful for making publication, and if anything, to give you a little bit of insight into the data that you're looking at. Okay, with that, I'll say that that pretty much ends the tutorial for today. I think these personally are just, my list of plugins that I would use, right? I like the violin box plots, I like the hyperfinder, but probably more so I like the clustering algorithms, FlowSum, XShift, and Phenograph in particular. And of course, the dimension reduction. t-SNE is my favorite, but of course you can use UMAP or TriMap as well. So if you guys have any questions, by all means, go ahead and ask. We'll try and run a UMAP here in the meantime, just for fun. But if you have any questions, go ahead and open up your mics, or go ahead and ask in the chat box, whatever you prefer. And then if this runs fast enough, I can just kind of show you what your t-SNE plot's going to look like versus your UMAP plot in the context of this experiment. Okay. I should also mention that this session has been recorded, so it will be available to you guys after today's session, probably a half hour to an hour. It takes a little while for Zoom to kind of put that, put the MP4, I think. It's either an MP4 or an MP3 file together. Once it does, then you basically get a link to it. And I think the link will last for 6 months, but you can download the whole MP3 if you want, and then that way you can host it forever. The other downside I would say about UMAP here is that you don't get a progress bar like you do with t-SNE, right? You kind of have an idea of like when it's going to finish. But in the case of UMAP, we're just sort of sitting here hoping that the computer is actually crunching the data. So UMAP used to be the fastest algorithm, but ever since opt-SNE came out in 2019, I think t-SNE has been faster. And so another reason why I prefer to use t-SNE, over UMAP. But again, it's really personal preference. Maybe you guys like to see those trajectories. All right, so I apologize. Again, it's, UMAP is slow, and we kind of would have to wait for it. But if you guys have any questions, go ahead and ask. If not, I'll go ahead and just say thank you very much for attending, and I wish you a great rest of your week. And go ahead and email me if you would like the link to this particular recorded session. So jack.flowjo@bd.com. Okay, I'm going to hang around a little bit here, maybe another minute or two, to see if UMAP will actually finish. calculating. Normally it seems, like it'll take a couple of minutes, but I've been surprised in the past where it's actually taken longer. All right, well, no help here from UMAP, so I'm going to go ahead and stop recording this session.